The universe's brightest giants hide its most baffling secrets. These supermassive stars, colossal engines of light and power, are not what they seem. They are cosmic anomalies, defying the very laws we thought governed stellar life. In this journey, you will uncover 30 of their most bewildering behaviors, from stars that flee galaxies at unimaginable speeds to explosions that rewrite stellar death. How can a star simply vanish without a trace? And what cosmic dance leads two giants to merge into one? What do you believe is the ultimate fate of these celestial titans? Our cosmic journey begins with a star on the run. Far from a serene celestial body, this is a fugitive, a runaway hypervelocity star blasting its way out of its home galaxy. Picture a stellar titan millions of times brighter than our Sun, being violently flung into the intergalactic void. The force required for such an expulsion is almost incomprehensible, and it points to a single, terrifying culprit, the supermassive black hole at the galaxy's heart. This is not a gentle nudge, it is a gravitational slingshot of epic proportions. One of the primary mechanisms behind this stellar eviction is known as the Hills mechanism. Imagine a binary star system, two stars locked in a mutual orbit, drifting too close to the dormant monster in the galactic center. The black hole's immense gravity can tear this partnership apart. One star is captured, falling into a tight orbit around the black hole, while its companion is hurled away at a staggering speed, often exceeding 1,000,000 miles per hour. A famous real-world example is the star known as S5HVS1, a supermassive star caught in the act of escaping our own Milky Way. It is racing outward at such a velocity that it will eventually leave our galaxy forever, destined to wander the cold, empty space between galaxies. What a lonely existence for a star born in a crowded stellar nursery. This dramatic escape reshapes our understanding of stellar life, proving that even the largest stars are not immune to the chaotic forces lurking in the cosmic dark. But that dramatic escape is only the beginning of the strangeness. While some stars are violently ejected, others are engaged in a more gradual, yet equally spectacular form of self-destruction. These giants are perpetually shedding their own substance, bleeding their mass into space at a rate that is almost impossible to fathom. Imagine a star so immense that it loses the equivalent of our entire planet Earth every single year. This is not a gentle evaporation, but a torrential, supersonic outflow of gas known as a stellar wind. The driving force behind this incredible mass loss is the star's own blinding light. The radiation pouring from its core exerts an immense outward pressure, a literal light power that overcomes the star's gravity and pushes its outer layers into the void. It is a constant, ferocious battle where the star's own energy is ripping it apart. This relentless shedding has profound consequences. It dramatically shortens the star's life, cutting short what is already a brief and brilliant existence. All that expelled material does not just vanish, however. It piles up around the star, creating vast, intricate nebulae that glow with eerie beauty. The Hubble Space Telescope has captured stunning images of these cosmic cocoons, like the one surrounding the star Eta Carinae, a nebula forged from its own titanic eruptions. These nebulae are more than just pretty pictures. They are the stellar graveyards and nurseries of the future, seeding space with the heavy elements necessary for new stars, planets, and perhaps even life itself. This shedding of mass can sometimes escalate into a full-blown stellar catastrophe. We now encounter one of the most volatile and unpredictable stars in the cosmos, the Luminous Blue Variable. These are the true divas of the stellar world, prone to spectacular, violent eruptions that defy all prediction. A single star can, without warning, increase its brightness by a factor of 100 or more, becoming one of the brightest objects in its entire galaxy for months or even years. During these giant eruptions, the star does not just bleed mass, it violently convulses, ejecting entire suns worth of material from its outer layers in a cataclysmic event. The fundamental mystery that baffles astronomers is the trigger. What could possibly cause a star to blow itself apart in such a dramatic fashion while somehow surviving the event? The most famous case study is the star Eta Carinae, right here in our own Milky Way. In the 1840s, it underwent what is now called the Great Eruption. For over 20 years, it outshone every star in the sky except for Sirius, despite being nearly 8,000 light-years away. It ejected at least 10 times the mass of our Sun, creating a vast bipolar cloud of gas and dust that now envelops it. This is the Homunculus Nebula, a cosmic hourglass visible through powerful telescopes. Before the eruption, Eta Carinae was a single, albeit unstable, point of light. After the eruption, it was encased in this beautiful, expanding tomb of its own making. The cause of this self-destructive fury remains one of astrophysics' greatest puzzles. Was it an internal instability, a near-violent pulsing as the star approached its theoretical luminosity limit? Or could it have been a stellar merger, a violent collision with a smaller companion star that provided a colossal injection of energy? The truth is, we still do not know what flips the switch on these stellar time bombs. While the eruptions of luminous blue variables are violent, they are not always final. For the very largest stars in the cosmos, however, there exists a death so absolute, so complete, that it erases them from existence entirely. This is the Pair-instability supernova, a theoretical explosion of unimaginable power reserved for stellar titans. The process begins deep within a star so massive that its core temperature soars to incredible heights. At these extreme energies, something bizarre happens to the very radiation that holds the star up. The gamma-ray photons, which provide the outward pressure against gravity, spontaneously transform into pairs of electrons and their antimatter counterparts, positrons. In an instant, the star's supporting radiation pressure vanishes. It is as if the floor has dropped out from under the core. Without that internal support, gravity wins decisively. The core collapses in a fraction of a second, but this collapse does not lead to a neutron star or a black hole. Instead, the infalling material compresses and heats up so rapidly that it triggers a runaway thermonuclear explosion. The entire star, from core to surface, is utterly annihilated. There is no remnant, no cosmic cinder left behind. The star is completely vaporized, its matter scattered back into the cosmos in a blast of pure energy. This ultimate stellar death is thought to have been common among the very first stars in the universe, monstrous giants composed only of hydrogen and helium. Their cataclysmic demises, visible across cosmic time, would have seeded the early universe with the first heavy elements, paving the way for everything that followed. To witness such an event would be to see a star not just die, but to be unmade, leaving nothing but a brilliant, fading echo in the void. Even the most violent stellar deaths leave behind a brilliant, fading echo. But some of these giants speak in a different language altogether, not with a final scream, but with a rhythmic, complex heartbeat. This is the mystery of quasi-periodic pulsations. Unlike the steady, predictable pulse of a variable star, these are strange, irregular rhythms of brightening and dimming. Imagine a star that breathes, but its breaths are deep, shallow, rapid, and slow, all in a seemingly chaotic sequence captured on a light curve graph as a wild, dancing line. The theories behind this stellar arrhythmia are as fascinating as the phenomenon itself. One leading idea points to massive, churning convection zones just beneath the star's surface. Think of it as a pot of water coming to a boil, with gigantic bubbles of hot plasma rising, cooling, and sinking back down in a turbulent, non-stop dance. This roiling motion causes the star's surface to heave and fall, changing its brightness in a complex quasi-periodic pattern. Another possibility involves non-radial pulsations, where the entire star does not simply expand and contract as a whole. Instead, different parts of its surface are oscillating out of sync. One hemisphere might be swelling outward while another is pulling inward. creating a complex interference pattern of light that we perceive as these erratic pulsations. For astronomers, these strange rhythms are not just noise, they are a celestial stethoscope. By carefully analyzing the intricate patterns in the light, scientists can literally listen to the interior of a star. Each specific pulsation frequency corresponds to vibrations traveling through different layers of the stellar interior. It is a form of asteroseismology, allowing us to probe the density, temperature, and composition deep within these opaque giants, mapping structures we could never otherwise see. This is how we learn what makes a star tick, or in this case, what makes its heartbeat so beautifully, mysteriously irregular. These irregular heartbeats are governed by forces far more powerful than mere gravity. Deep within some stellar giants, invisible monsters are at work, magnetic fields of almost incomprehensible strength. These are not the simple, orderly fields of a bar magnet, but chaotic, dynamic webs of power that can be billions of times more intense than the magnetic field of our own sun. At such magnitudes, magnetism ceases to be a background force and becomes the primary architect of the star's appearance and destiny. It sculpts the very substance of the star, warping its atmosphere and dictating the flow of its cosmic winds. A perfect example is the brilliant star Theta-1 Orionis C, the most luminous star in the famous trapezium cluster at the heart of the Orion Nebula. Its magnetic field is a titanic structure, and it does not act symmetrically. Instead, this immense force channels the star's ferocious stellar wind, funneling it outward from the star's magnetic poles. This creates two opposing supersonic jets of gas screaming into space, while at the magnetic equator, the wind is stifled to a relative whisper. This magnetic control also creates bizarre surface features. The field forces incredibly hot gas to accumulate at the magnetic poles, generating searing bright spots, far hotter and brighter than the rest of the star's surface. As the star rotates, these blazing hotspots sweep into and out of our view, causing the star's brightness to pulse in a regular, predictable rhythm. We are essentially seeing a star with two colossal, permanent searchlights fixed to its poles. The influence of such a magnetic monster extends throughout the star's entire life. By channeling mass loss so efficiently, it strips away the star's outer layers at an accelerated rate, dramatically altering its future evolution and ultimate fate. The entire life story of the star is rewritten by this invisible, internal cage of pure force. These invisible magnetic cages can sometimes fling an entire star's atmosphere into orbit. We now meet the B stars, a class of supermassive, rapidly spinning giants that perform a bizarre act of cosmic disassembly. They sporadically eject their own outer layers, not in a spherical wind, but to form a vast, glowing disk of gas that circles the star like a fiery Saturn ring. The key to this strange behavior is rotation. These stars spin at truly breakneck speeds, often so fast that they are on the verge of tearing themselves apart. This rapid rotation flings material outward from the equator, a process fundamentally governed by centrifugal force. Imagine swinging a bucket of water on a rope in a wide circle. The water presses against the bottom of the bucket, held in by the force of the spin. Now picture a star where the gravity at its equator is almost overcome by its own dizzying rotation. The outer layers of gas become that water in the bucket, eager to fly off into space. This ejected material does not escape entirely. Instead, it settles into a stable, rotating disk around the star's middle. This circumstellar disk is the defining feature of a B star, and it leaves a clear fingerprint in the starlight we observe. When astronomers split that light into a spectrum, they see bright emission lines superimposed on the star's normal rainbow of colors. These lines are the direct result of the disk itself glowing, a tenuous cloud of hydrogen gas being energized by the star's intense ultraviolet radiation. The presence of these emission lines is what gives the B stars their name. The behavior of this disk is anything but stable. It can appear, grow, shrink, or even vanish over timescales of months or years, leading to unpredictable changes in the star's observed brightness. As the disk grows denser, it blocks more of the star's light when viewed edge-on, and when it dissipates, the star appears to brighten again. This cyclical process of ejection and reaccretion makes these stars notoriously variable and difficult to classify with certainty. A star might be classified as a standard B-type star 1 year, and then, after a major ejection event, it transforms into a B star with a prominent disk, only to revert back years later. This constant state of flux challenges our simple categorizations, reminding us that these giants are dynamic, living entities, constantly reshaping themselves and their immediate surroundings. This self-stripping process reaches its ultimate, violent conclusion with the Wolf-Rayet star. These are stellar corpses walking, stars that have violently torn away their own outer flesh to expose the searing hot elements of their core. A normal supermassive star is wrapped in a thick blanket of hydrogen, but a Wolf-Rayet has shed this entirely, either through ferocious stellar winds or in a cataclysmic eruption. What remains is a bare, blistering engine, an exposed stellar core with a surface temperature soaring above 100,000 degrees Celsius. Its atmosphere is now a bizarre and exotic mix, no longer dominated by hydrogen but by the products of nuclear fusion, helium, carbon, and nitrogen. The light from such a star tells a story of extreme violence. When astronomers spread its light into a spectrum, they do not see the dark absorption lines typical of most stars. Instead, they see broad, brilliant emission lines, a screaming signature of its turbulent, expanding atmosphere. These thick, smeared lines are created by the star's phenomenal winds, which blast material into space at speeds approaching 10 million miles per hour. This wind is so dense and moving so fast that the gas glows brightly itself, creating the emission lines, and the tremendous speed smears them out, making them wide and blunt on the spectrum. This is the star's death cry, written in light. The visual evidence of this self-destruction is equally stunning. The Crescent Nebula is a vast, delicate shell of gas sculpted by the wind from a central Wolf-Rayet star. This is not a remnant from a supernova, it is the accumulated debris from the star's own continuous, epic shedding of its mass. These stars are living on borrowed time, and their fate is sealed. A Wolf-Rayet is a direct precursor to a core collapse supernova. Having already expelled its hydrogen envelope, the resulting explosion will be a type Ib or type Ike supernova, a different, hydrogen-free kind of stellar death. To observe a Wolf-Rayet is to look at a star in its final act, a titan that has already dismantled itself, now shining with the brilliant, exposed heat of its own imminent demise. The line between a star's final death cry and a violent temper tantrum is far blurrier than we ever imagined. Some of the most brilliant stellar outbursts recorded are not supernova at all, but brilliant, deceptive fakes known as supernova impostors. These events mimic the cataclysmic explosion of a dying star, releasing a tremendous flash of light that can outshine entire galaxies for months. The stunning twist is that when the light fades, the star is still there, having somehow survived its own apparent self-destruction. These impostors are now strongly linked to the most unstable luminous blue variables, representing their most extreme, eruptive episodes. It is a star pushing itself to the absolute limit, ejecting multiple times the mass of our Sun, yet somehow holding its core together. This phenomenon directly challenges the very definition of a supernova, forcing us to ask what truly constitutes a stellar death. The incredible story of one object known as SN 2009 IP perfectly illustrates this mystery. Initially spotted in 2009, it was first classified as a supernova, but then it did something unprecedented. It faded, only to erupt again in 2011. This was no ordinary star death. This was a star having repeated violent outbursts. For 3 years, it continued this bizarre performance, flaring up dramatically before settling down. Astronomers watched utterly captivated as it became clear they were witnessing a prelude to a true catastrophe. Then, in 2012, SN 2009 IP erupted with a ferocity that seemed final. The light curve and spectra screamed supernova, and many believed the star had finally torn itself apart. Yet for years, debate raged. Had it truly died, or was this just its most powerful fake out yet? The consensus now points to that final event being the real deal, a genuine core collapse supernova. The preceding outbursts were the star's desperate, final acts of self-cannibalization, shedding enormous amounts of material in a series of violent rehearsals before the true finale. This sequence of events paints a new, more complex picture of how the most massive stars die, not always with a single bang, but sometimes with a dramatic, drawn-out performance of false endings and final bows. The gravitational dance between two supermassive stars is a delicate and often destructive tango. In a binary system, these stellar titans are locked in a close orbital embrace, bound by gravity yet constantly battling for dominance. Their interaction creates a bizarre cosmic phenomenon known as the Roche lobe. Imagine a teardrop-shaped bubble of space surrounding each star, a zone where its gravity is the dominant force. The point where these two lobes meet is like a cosmic watershed, a gravitational saddle point where material can flow from one star to the other. When one star in the pair, bloated by age and expansion, grows so large that its outer atmosphere spills over this boundary, the strange transfer of mass begins. A river of stellar gas comprised of hydrogen and helium streams from the inflated donor star directly onto its companion. This process, called Roche lobe overflow, completely rewrites the life story of both stars. The star losing mass is being stripped of its outer layers, potentially exposing its hot core prematurely. The star gaining this material, however, is being rejuvenated. It gains a fresh coat of hydrogen fuel which can reignite nuclear fusion in its core and spin it up to incredible velocities. This is not a gentle rain, it is a torrential downpour of stellar matter. As this stream of gas slams onto the surface of the receiving star or forms a hot, spinning disk around it, the material compresses and heats to millions of degrees. In systems where the receiving star is a dense neutron star or a black hole, this process generates some of the most energetic phenomena in the universe, X-ray binaries. These are cosmic lighthouses beaming high-energy radiation across the galaxy, powered entirely by this gravitational feeding. The ultimate consequence of this stellar theft can be even more dramatic. In certain binary systems containing a white dwarf, the dead core of a star like our Sun, the steady accumulation of stolen mass can push it over a critical threshold. When the white dwarf reaches about 1.4 times the mass of our Sun, the pressure and temperature in its core become so extreme that carbon fusion ignites almost instantly. This triggers a runaway thermonuclear explosion that completely obliterates the white dwarf in a Type Ia supernova. This specific type of explosion is so uniform in its brightness that astronomers use it as a standard candle to measure vast cosmic distances. The very structure of our expanding universe was mapped using these stellar explosions, all born from the final, catastrophic act of a binary star's gravitational dance. The stellar theft of a binary system seems almost orderly compared to the next cosmic mystery. Some supermassive stars do not simply erupt or explode, they vanish. A star can be shining steadily for years, a constant point of light, and then, without any warning, its brightness plummets. It dims by a factor of 100 or even 1,000, fading into near invisibility before slowly, mysteriously recovering its former glory. This is the bizarre behavior of an Coronae Borealis variable star. The leading suspect in this great disappearance is a cloud of cosmic soot. These stars are carbon-rich giants, and astronomers believe that at unpredictable intervals, conditions in their upper atmospheres become just right for carbon atoms to condense, forming a cloud of solid graphite dust like the lead in a pencil. This cloud does not form far away, it materializes right there, blanketing the star's surface. It is as if the star has suddenly blown a colossal puff of black smoke, obscuring its own light. The star is still shining just as brightly underneath, but we cannot see it. The mystery is what flips the switch, what triggers the sudden condensation of this light-blocking shroud. It could be linked to a violent pulsation, a heaving of the star's outer layers that cools the gas just enough for carbon to solidify. Or perhaps it is a magnetic event, a stellar flare that churns the atmosphere into the perfect state for dust formation. The recovery is just as strange. The star does not just sit there under its blanket of soot. Its intense radiation pressure, the sheer force of its light, eventually pushes the cloud of dust away, dispersing it into the void and allowing the star's full brightness to return. This creates the most dramatic light curves in all of astronomy. A graph of the star's brightness over time does not show a gentle wave, it shows a deep, jagged canyon, a vertical drop into darkness followed by a slow, irregular climb back to the light. The entire process is chaotic and utterly unpredictable. One famous star, RY Sagittarii, can remain at maximum brightness for years before plunging into a deep minimum that lasts for months. To witness such an event is to watch a star play peek-a-boo with the universe, cloaking and uncloaking itself in a shroud of its own making. That cosmic game of peek-a-boo is a gentle flicker compared to the ultimate stellar detonation. Some supermassive stars are the secret progenitors of the single most powerful explosion since the Big Bang itself, the long-duration gamma-ray burst. For a few fleeting seconds, these events can outshine every star in a billion galaxies combined, releasing more energy than our Sun will emit in its entire 10 billion-year lifetime. The engine for this unimaginable violence is the death of a very specific kind of star, one that is not only supermassive but also spinning at a ferocious speed. When such a star finally exhausts its nuclear fuel, its core collapses directly into a black hole. But this is not a quiet collapse. The star's immense rotational energy, its stored spin, cannot simply vanish into the void. Instead, it is focused. This energy is channeled along the star's rotation axis, launching a pair of ultra-relativistic jets, beams of matter and radiation screaming outward at over 99.9% of the speed of light. These jets are like cosmic blowtorches drilling their way through the star's outer layers. If one of these jets is pointed directly at Earth, we detect its initial blinding flash of high-energy gamma rays. That initial flash is just the beginning. As the jets plow into the surrounding interstellar gas, they create a brilliant, long-lasting afterglow visible across the electromagnetic spectrum, from X-rays to radio waves. This is the stellar death cry writ large across the cosmos. What makes this even more profound is the intimate connection to a supernova. The same collapsing star that creates the black hole and jets also triggers a colossal supernova explosion. We have observed this directly, seeing the characteristic signature of a supernova emerge in the afterglow of a gamma-ray burst. It is a two-stage death, a supernova heralding the birth of a black hole, which in turn unleashes the universe's most focused and furious beams of energy. To witness such an event is to see a star die twice, first with a brilliant flash that rewrites the rules of power, and then with an expanding cloud of debris that seeds the galaxy for the future. The very substance of a star holds the key to its ultimate fate. Within the heart of every supermassive giant, the concentration of metals, which astronomers define as any element heavier than helium, dictates a dramatic divergence in behavior. This cosmic chemistry, the star's metallicity, controls the most fundamental aspects of its life, from the ferocity of its winds to its final, cataclysmic death. Consider two otherwise identical stellar titans. The one born in a modern, metal-rich galaxy like our Milky Way is cloaked in a haze of heavier elements. These atoms are incredibly efficient at absorbing the star's intense radiation, When this absorbed light is re-emitted, it transfers momentum to the gas, pushing it outward in a powerful, relentless stellar wind. This star bleeds mass at a phenomenal rate, constantly shedding its outer layers and limiting its own growth. It is a case of cosmic self-sabotage, where its own chemical richness leads to a more rapid and dramatic demise. Now picture its counterpart, a star born in the early universe from primordial gas, a composition almost purely of hydrogen and helium. This low metallicity star is transparent to its own radiation. Its light passes through the outer layers with far less interaction, resulting in a much weaker stellar wind. Without this powerful outflow to strip it away, the star can hold onto its mass, potentially ballooning to sizes we once thought impossible. It is a stable, efficient, and terrifyingly massive engine. This fundamental difference reshapes our understanding of cosmic history. The first stars in the universe, known as population 3 stars, were likely all low metallicity monsters. They grew to staggering sizes, some perhaps reaching several hundred times the mass of our Sun. Their lives were brief and brilliant, ending in those pair-instability supernova that completely vaporized them, seeding the cosmos with the first heavy elements. Every metal in your body, the iron in your blood, and the calcium in your bones was forged in such a star or in the explosion that ended it. As the universe became enriched with these metals, later generations of stars, like those we see today, were born with built-in limitations. Their own chemical richness ensured they could not grow to the same monstrous proportions as their ancient ancestors. The environment of a star's birth, therefore, writes the first and most crucial chapter of its life story, a narrative of wind, mass, and cosmic legacy written in the language of elemental chemistry. The chemistry of a star's core dictates its final fate, but some giants hide a far stranger engine. Deep within a supermassive star, a neutron star can orbit as a captive core, a bizarre hybrid known as a Thorn-Zitkow object. This is not a simple binary system. It is a star within a star, a Russian nesting doll on a cosmic scale. The formation of such a monster requires a very specific and violent sequence of events. It begins with a tight binary system where one star is slightly more massive and evolves faster, exploding as a supernova and leaving behind a dense neutron star. If the explosion does not kick the system apart, the neutron star remains bound to its supermassive companion. As this companion ages and swells into a red supergiant, its outer envelope expands to engulf its tiny, ultra-dense neighbor. The neutron star spirals inward through the tenuous outer layers, eventually settling at the very heart of the giant, becoming a new kind of core. This neutron star core does not just sit there, it radically alters the star's internal chemistry. The intense gravity and heat at the surface of the neutron star create a unique cauldron for nucleosynthesis, the process of forging new elements. In a normal supermassive star, heavy elements like rubidium, lithium, and molybdenum are produced in trace amounts. But in a Thorn-Zitkow object, the extreme conditions around the neutron core are predicted to overproduce these specific elements, along with many others, creating an exotic and unmistakable chemical fingerprint. The star's outer atmosphere would become heavily enriched with these unusual isotopes. For decades, astronomers have searched for this predicted chemical signature. The challenge is immense, as a Thorn-Zitkow object would look at first glance almost identical to a regular red supergiant. Its light would be red and cool, and it would pulsate gently. The only way to distinguish it is through a detailed analysis of its spectrum, hunting for those telltale overabundances of rare elements. A few candidates have been proposed, like the red supergiant star HV 2117 in the Small Magellanic Cloud, which showed unusual abundances of lithium and molybdenum. The evidence, however, was not conclusive enough for a definitive discovery. The hunt continues for this stellar chimera, a ghost in the data that would confirm one of the most peculiar structures a star can possibly possess. That ultimate detonation can be dwarfed by an even more catastrophic end. A hypernova is a supernova on steroids, an explosion so energetic it redefines the limits of stellar violence. This is the death scream of a star at least 25 times more massive than our Sun, a true leviathan whose core collapse is anything but ordinary. The engine behind this cosmic cataclysm is the collapsar model. When such a star reaches the end of its life, its iron core is so immense that it does not form a neutron star. Instead, it collapses directly without pause into a black hole. The sheer mass plunging inward creates a gravitational well of unimaginable depth, and the energy released in this single, swift act of creation is staggering. But the collapse is not perfectly spherical. The star's rapid rotation, a vestige of its birth, twists the infalling material into a furious, superheated accretion disk that swirls around the newborn black hole. This disk is the true power source. Friction within this maelstrom of matter heats it to billions of degrees, launching jets of plasma and radiation from its poles at nearly the speed of light. These jets, focused and deadly, blast their way out through the star's outer layers, and it is this focused beam that we often observe as a long-duration gamma-ray burst. The rest of the star, meanwhile, is torn apart by a shock wave of unbelievable force, resulting in the hypernova explosion itself, a blast that can be 10 times more luminous than a typical core collapse supernova. We have likely witnessed the aftermath of such events. The famous supernova SN 1998 BW, which was detected in conjunction with a gamma-ray burst, is a prime candidate. Its explosion was extraordinarily powerful, and its expanding debris cloud moved at a significant fraction of light speed, both hallmarks of a hypernova. Advanced computer simulations allow us to peer into the heart of this chaos. They show the iron core vanishing into nothingness in milliseconds, the instantaneous birth of a black hole, and the subsequent formation of the furious accretion disk. The simulations trace the jets as they burrow outward, taking only seconds to rip the star apart from the inside. To see such a simulation is to watch a star die twice at once, collapsing into a singularity while simultaneously being eviscerated by the very energy its own death released. A star's violent end can be a drawn-out performance of false finales. Pulsational pair-instability is the cosmic drama of a star dying in fits and starts, a series of colossal eruptions that tear it apart layer by layer before its final surrender. This fate befalls only the most massive stars, those weighing between 100 and 130 times the mass of our Sun. Deep within such a titan, the core temperature soars so high that gamma-ray photons, the very things providing outward pressure, spontaneously create matter. They transform into pairs of electrons and positrons. This act of creation is a catastrophic theft. The radiation pressure that was holding the star up against its own gravity suddenly plummets. The core, now unsupported, begins a violent collapse, but unlike in a single, final pair instability event, this core is just below the total annihilation threshold. It does not explode completely. Instead, the collapse heats the core even further, reigniting nuclear fusion in a ferocious runaway burst. This new wave of energy is so powerful that it does not just stop the collapse, it blows the star's outer layers clear off in a massive eruption. This is the first pulse. The star ejects many solar masses of material into space in a pseudo-supernova, an explosion that can outshine entire galaxies. Yet, miraculously, the core survives. It continues burning, now exposed and reset. The star then goes through a period of relative calm, slowly building up pressure and temperature once more until the cycle repeats. The same instability triggers another collapse, another violent reignition, and another pulse that ejects more of its remaining mass. A single star might endure half a dozen of these apocalyptic convulsions over decades or centuries, each one a rehearsal for the final act. The evidence for this staggered death is written in the light we observe. The supernova light curve, a graph of its brightness over time, does not show a single, clean peak and a steady decline. Instead, it reveals a jagged landscape with multiple secondary peaks and plateaus. Each bump corresponds to the expanding shell of gas from a previous pulse being slammed into by the ejector from a later eruption. It is a cosmic traffic jam of stellar debris, with successive shock waves re-energizing the expanding material and causing the dying star to flare brightly over and over. Observing such an event is like watching a series of massive waves crashing on a shore, each one building on the energy of the last, a drawn-out and spectacularly violent farewell to one of the universe's true giants. A star can steal more than just mass from its companion. This gravitational theft also transfers a hidden form of energy, angular momentum, spinning the thief up to a dizzying, destructive velocity. In a cosmic twist, the act of feeding makes the vampire star itself unstable. As material flows from the donor star, it does not fall directly onto the surface of the hungry giant. Instead, it forms a whirling, superheated disk of gas known as an accretion disk, a vortex of stolen matter spiraling inward. This incoming material carries with it the orbital momentum of its previous path, and as it crashes onto the receiving star, it delivers a continuous spin-up effect, much like a constant push on a merry-go-round. The star's rotation accelerates faster and faster until it is spinning at a significant fraction of its breakup speed, the point where centrifugal force would overcome gravity and tear it apart. This extreme rotation has dramatic, visible consequences. The star is no longer a sphere. It bulges dramatically at its equator, becoming an oblate spheroid, a shape like a spinning beach ball someone is sitting on. This flattening is so pronounced that the star's poles are significantly closer to its core than its equator, creating a stark temperature difference. The poles, under greater gravitational pressure, become hotter and brighter while the bloated equator is cooler. This phenomenon, known as gravity darkening, means the star's appearance and temperature are entirely dependent on your viewing angle. Look at it from the equator and it appears cooler and dimmer. Observe it from the pole and you are staring into a searing, brilliant hotspot. This rapid spin also churns the star's interior in a process called rotational mixing. Elements forged in the nuclear furnace of the core, like helium and nitrogen, are dredged up to the surface, while fresh hydrogen from the outer layers is dragged down to the core. This internal recycling fundamentally alters the star's surface chemistry and extends its life by providing more fuel to the core. The entire evolutionary pathway of the star is rewritten, not just by the mass it steals, but by the furious, relentless spin that the theft imposes. This vampiric relationship is a temporary state, a prelude to a far more violent end for both stellar partners. This stellar vanishing act is not always a performance. Sometimes a star simply disappears. For a supermassive star, the ultimate fate is a brilliant supernova, a final, defiant flash that illuminates the cosmos. But some of these giants cheat the light, vanishing in the most unsettling way possible through a failed supernova. In this eerie scenario, a star massive enough to explode simply winks out of existence, collapsing directly into a black hole without a firework display. The conditions for this silent death are brutally specific. The star must possess a very massive core, one rich in heavy elements like oxygen and neon. As this core collapses at the end of the star's life, it encounters a runaway wave of neutrino production. In a normal supernova, these ghostly particles carry away the immense energy of the collapse, but their outward pressure is what helps blow the star's outer layers into space. In a failed supernova, the core is so incredibly heavy that the sheer force of its own gravity overwhelms everything. The neutrinos, trillions of them, are trapped and dragged back inward by the immense gravitational pull. With no outward pressure to halt the collapse, the entire stellar core plunges past the point of no return in a matter of seconds. It simply implodes, leaving behind a newborn black hole where a star's heart once beat. The outer layers of the star, suddenly with nothing to support them, feel the full, unrelenting pull of this new singularity. They begin to fall inward, a silent, dark avalanche of gas. But as this material spirals down toward the event horizon, it compresses and heats up, potentially releasing one final, faint glimmer of light, a dim red flash that is 1,000,000 times fainter than a true supernova. Then nothing, the star is gone. Observing this phenomenon is one of modern astronomy's greatest challenges. You are looking for something that is not there. The most compelling potential case is a star known as N6946bH1, located in the Fireworks galaxy about 20 million light-years away. Astronomers were monitoring this red supergiant, a star about 25 times the mass of our Sun. It was a bright, steady point of light. Then, in 2009, it flared up modestly, becoming about 1,000,000 times more luminous than the Sun for a few months. This could have been the star's last feeble struggle, the final ejection of material before the core's collapse. After that flare, it simply vanished. The before and after images are haunting. In the before picture, the star is clearly visible. In the after picture, taken with the Hubble Space Telescope, there is only empty space. Follow-up observations with the Large Binocular Telescope and the Spitzer Space Telescope scoured the location in infrared light, searching for any hidden remnant or dust-shrouded survivor. They found nothing. The star was gone, and in its place, only the profound darkness of a new black hole remains. This discovery suggests that a significant number of massive stars may end their lives in this quiet, dark manner, slipping away from the universe without a final goodbye. How many other stellar giants have simply turned off their lights, leaving behind only gravitational ghosts for us to somehow one day find? These ghostly disappearances leave behind a profound silence, but the atmosphere of a supermassive star is anything but quiet. Its light carries a hidden language, a spectral fingerprint that can flicker and change with bewildering speed. The rainbow of colors emitted by a star is not a smooth continuum. It is scarred by dark absorption lines and bright emission lines, each telling a story about the elements in its atmosphere. For most stars, this pattern is stable, a constant signature, but for some supermassive giants, this spectrum is in constant, chaotic flux. Emission lines can vanish in hours only to reappear days later. Absorption lines can dramatically shift back and forth, and entirely new lines can materialize from nowhere. This bizarre spectral variability is the star's atmosphere screaming in a state of violent upheaval. One of the primary culprits is a clumpy stellar wind. We often picture a star's wind as a smooth, continuous outflow of gas, but the reality is far more turbulent. The wind is actually a storm of massive, discrete blobs and shocks. Imagine a fire hose not spraying a steady stream, but firing cannonballs of superheated plasma. When one of these dense clumps is ejected, it can produce a temporary, bright emission line as the gas glows. As it moves away and dissipates, that line fades. The constant ejection of new clumps creates a strobing effect in the spectrum, with lines blinking on and off in a chaotic rhythm. Time series spectroscopy, which is like taking a high-speed video of a star's spectrum, captures this incredible dance. The resulting data visualizations are not static images, but dynamic maps of light, showing lines that writhe, intensify, and vanish across the timescale of a single night. This reveals that the star's atmosphere is not a placid layer of gas, but a seething, storm-racked frontier where material is being violently ejected in fits and starts. These rapid changes are also tied to the star's deep, resonant pulsations. As the entire star breathes, heaving its surface inward and outward, the density and temperature of its atmosphere swing wildly. This can cause certain elements to ionize or recombine, effectively turning their spectral lines on and off like a switch. A magnetic field adds another layer of complexity, creating bright, hot spots that rotate in and out of view. each with its own unique chemical signature that imprints itself on the spectrum before vanishing again as the star spins. Decoding this frantic light show allows astronomers to do more than just identify elements. It lets them map the star's atmospheric weather in real time, witnessing the violent, unpredictable storms that rage across the surface of a cosmic giant. That frantic light show in a star's atmosphere is a prelude to its final, spectacular performance. Some stellar deaths are not merely bright, they are superluminous, shining with the power of 10 or even 100 normal supernovae. These are cosmic beacons that can outshine their entire host galaxies for months, and their incredible power forces us to rethink the very physics of stellar death. The key to understanding these events lies in their unique light curve, the graph of their brightness over time. A normal supernova peaks quickly and then fades in a steady, predictable decline. A superluminous supernova, however, climbs to a staggering peak and then lingers, its light curve forming a broad, high plateau that can last for over 100 days before slowly dimming. This extended brilliance means a conventional radioactive decay model cannot be the sole power source. There must be something else, a central engine or an external interaction, pumping immense energy into the expanding debris. One of the leading theories is the circumstellar interaction model. This scenario suggests that before its death, the star was not stable. It was a luminous blue variable or a Wolf-Rayet star, violently shedding its outer layers in repeated eruptions. These outbursts created a series of dense, massive shells of gas surrounding the star, like a set of cosmic Russian nesting dolls. When the star's core finally collapses and triggers the supernova, the resulting explosion slams into these pre-existing shells at incredible speeds. The collision is ferocious, converting the kinetic energy of the blast into a tremendous, sustained outpouring of light. It is like throwing a lit match into a trail of gasoline you have already poured. The resulting fireball is far larger and longer lasting than the match alone could ever produce. Another compelling explanation involves a powerhouse known as a magnetar engine. In this model, the collapsing core of the supermassive star does not form a simple neutron star. It forms a magnetar, a neutron star spinning hundreds of times per second and possessing a magnetic field a quadrillion times stronger than Earth's. This spinning magnetic dynamo acts like a continuous battery, dumping colossal amounts of rotational energy into the supernova ejector. This injected energy keeps the expanding cloud hot and luminous for months, creating that characteristic broad plateau in the light curve. It is the difference between a single firecracker and a flare attached to a continuous fuel supply. The star's pre-death behavior is the crucial link. A star that calmly burns through its fuel might produce a standard supernova, but a star that has experienced violent pulsations, extreme mass loss, or a history of giant eruptions sets the stage for a far more spectacular finale. Artist depictions of these events try to capture their impossible scale, showing a central, blistering point of light, the magnetar engine or the collision shock embedded within a nebula of expanding debris so bright it washes out the surrounding stars. To witness such an event would be to see a star die not with a bang, but with a sustained, universe-defining roar that challenges our understanding of cosmic power. These chaotic stellar atmospheres can be a prelude to the most intimate of cosmic collisions. When two supermassive stars are locked in a tight binary dance, their gravitational embrace can end not in a gentle transfer of mass, but in a violent head-on merger. This is not a slow, graceful spiraling, but a final, catastrophic union that forges a single, even more colossal star from the wreckage of two. The process begins as the stars slowly lose orbital energy, inching closer over millennia. As their surfaces finally touch, a terrifyingly beautiful sequence unfolds. Their outer layers violently shred, spilling into a shared, turbulent envelope of superheated gas that engulfs both cores. Inside this common envelope, the two stellar cores are now trapped, orbiting each other within a seething, chaotic shroud. Friction with this dense gas acts as a cosmic brake, relentlessly sapping their orbital energy. The cores spiral inward faster and faster on a collision course. In the final moments, the two cores plunge into one another, their immense masses colliding and fusing. The energy released in this impact is staggering, rivaling a supernova for a brief, brilliant instant. We have witnessed the aftermath of such an event. The star V1309 Scorpii was for years an unremarkable variable star. Then, in 2008, it did something extraordinary. Over just a few months, its brightness skyrocketed by a factor of 30,000, becoming 1,000,000 times more luminous than our Sun before fading away into a red, dusty cloud. Astronomers studying old data realized this was not a supernova, but a luminous red nova, the direct and spectacular signature of two stars merging into one. The light curve was the telltale clue, a sharp, exponential rise in brightness followed by a slow, cool decline, perfectly matching predictions for a stellar merger. This event also provides a tantalizing glimpse into the future of gravitational wave astronomy. While our current observatories like LIGO are tuned to the high-frequency ripples from merging black holes and neutron stars, a supermassive stellar merger would produce a low-frequency rumble, a gravitational wave signature that future space-based detectors like LISA will be able to hear. The violent spiraling of two massive cores within their common envelope would send a unique, churning signal across spacetime. Advanced computer simulations allow us to visualize this incredible chaos, showing the two stars distorting into teardrop shapes, their material being drawn out into spiraling arms before the final, cataclysmic convergence into a single, bloated object. The outcome of this cosmic forging is as unpredictable as it is violent. The merger might create a single, rejuvenated supermassive star, its outer layers stripped away to reveal a hot, rapidly spinning engine. It could trigger a massive eruption, ejecting a shell of debris that glows as a new nebula. Or, if the combined mass is too great, it might immediately collapse into a black hole, a silent end to a spectacularly loud event. Each merger is a unique experiment in stellar physics, rewriting the life story of two stars in a single, violent chapter. An aging supermassive star can reverse its own cosmic clock. After spending its hydrogen fuel and swelling into a red supergiant, you would expect it to simply cool and expand further until its final death. Yet for many of these giants, the story takes a bizarre turn. As helium fusion ignites in the core, the entire star contracts and heats up dramatically. It abandons its red supergiant status and moves back across the Hertzsprung-Russell diagram, tracing a path toward the blue, hotter region in what astronomers call a blue loop. This is not a simple backtracking, it is a complex stellar recalibration. The star becomes smaller, hotter, and bluer for a significant portion of its helium-burning life, a phase that can last millions of years. The driving force behind this loop is a delicate balancing act between the star's core and its vast envelope. When helium fusion begins, it does so in a shell around an inert core of carbon and oxygen. This new energy source alters the delicate balance between pressure and gravity. The core actually contracts, becoming hotter and more efficient. This contraction releases gravitational energy that makes the outer layers of the star shrink and heat up as well, pulling the star away from the cool, red side of the diagram and back toward the blue. Evolutionary track diagrams, which chart a star's temperature against its luminosity, vividly illustrate this journey. Instead of a smooth, direct path from the main sequence to the red supergiant branch, the line curves sharply, hooking back to the left before eventually returning to the red giant region. It literally draws a loop on the graph. This looping behavior is not guaranteed for every star. It depends critically on two factors, mass and metallicity. A star must be sufficiently massive, typically between 8 and 25 solar masses, to experience this phenomenon. Stars of lower mass simply do not have the internal conditions to trigger such a dramatic response. Metallicity, the abundance of elements heavier than helium, is equally crucial. In a high metallicity star, like those common in our modern Milky Way, the atmosphere is opaque due to all the heavy elements. This opacity makes stellar winds stronger and the outer envelope more bloated, which actually suppresses the blue loop. The star is too puffed up to contract effectively. In contrast, a low metallicity star, similar to those from the early universe, has a more transparent atmosphere. It can shed its outer layers more efficiently and contract more readily, making a pronounced blue loop far more likely. This means that by observing where a supermassive star sits on this loop, we can deduce not only its current phase but also the chemical history of its birth environment. It is a celestial signature written in temperature and light, a temporary return to youth before the final, irreversible slide into stellar old age. That sudden return to youth can be a violent, messy process. For some supermassive stars, mass loss is not a steady breeze but a series of hurricane-force outbursts, where they violently eject entire shells of their own substance into space. This episodic mass loss carves the star's history into the surrounding nebula, leaving behind a fossil record of its instability. The trigger for these dramatic expulsions often lies deep within, in the unstable nuclear furnaces known as burning shells. Imagine a star like a complex onion with layers of different elements fusing at different depths. Outside the inert core, a shell of helium may be burning fiercely. This shell is not always stable. It can pulse, burning in fits and starts. During a pulse, a wave of energy and pressure surges outward, violently pushing on the star's enormous envelope. This thermal pulse can be so powerful that it heaves the star's outer layers right off, launching a colossal shell of gas at incredible speeds. The historical record of the star P Cygni is a perfect testament to this behavior. In the early 17th century, this star appeared out of nowhere, becoming a bright, new star in the constellation Cygnus. Over the following decades, it underwent several dramatic outbursts, fading and brightening erratically as it ejected shell after shell of material. Today, P Cygni is classified as a luminous blue variable, a star notorious for such violent episodes. Modern observations reveal the beautiful aftermath of this chaos. High-resolution images show multiple, faint concentric shells of gas expanding away from the star. These are not smooth bubbles, they are clumpy, irregular structures, each one a ghostly echo of a past eruption. It is as if we are looking at a stellar tree ring, where each ring marks a moment of internal upheaval and violent release. The star is quite literally writing its autobiography in blown-off layers of gas, a story of repeated internal rebellion that shapes its final, explosive destiny. A star's solitary journey is often an illusion. Many of the most bizarre stellar behaviors we have explored are not solo acts, but the product of a gravitational duet. Being locked in a binary or multiple star system can induce, amplify, and completely reshape the strange life of a supermassive star. The constant, close proximity dance creates a dynamic environment where tides, mass transfer, and mutual irradiation rewrite the rules of stellar evolution. Tidal forces alone can work profound changes. The gravitational pull from a companion star stretches its partner, distorting its perfect sphere into a teardrop shape. This constant tugging churns the star's interior, stirring up its nuclear burning layers and altering its internal chemistry and rotation in a process called tidal mixing. It can even synchronize the star's spin with its orbit, forcing it to always show the same face to its partner, much like our moon does with Earth. This distortion alone can trigger unexpected pulsations or enhance mass loss from the star's gravitationally stretched equator. But the real drama begins with mass transfer. When one star in the pair evolves and swells, its outer atmosphere can spill over the gravitational boundary of its roche lobe, pouring a river of its own substance onto its companion. This act of stellar theft is a transformative event for both stars. the donor star is stripped of its outer hydrogen layers, potentially revealing its hot helium core prematurely and turning it into a Wolf-Rayet star far earlier than if it were alone. The recipient star, meanwhile, is force-fed. It gains a fresh coat of hydrogen fuel which can rejuvenate it, spinning it up to incredible speeds and making it appear younger and more massive than it truly is. This can turn a stable star into a volatile, rapidly rotating beast prone to outbursts. The system known as Beta Lyrae is a perfect example of this combined weirdness. Here, two massive stars are so close that they are actively feeding off each other, surrounded by a thick, shared disk of gas. The mass transfer has been so extensive that the more massive star has actually transferred most of its envelope to the lesser star, inverting their expected roles. The system is enshrouded in this torus of gas, which eclipses the stars from our view and creates one of the most peculiar and complex light curves known. Animations of such binary interactions reveal the beautiful chaos. We can watch as one star bloats into a red supergiant, its outer layers spilling through the narrow point between the two gravitational spheres. A luminous stream of plasma, like a celestial umbilical cord, connects the two bodies. The incoming material forms a brilliant, spinning accretion disk around the receiving star, glowing with intense heat from the friction of the spiraling gas. In some extreme cases, this entire process can culminate in a merger, a final, violent embrace that forges a single, even more massive and unstable star, setting the stage for a future hypernova or gamma-ray burst. The presence of a companion is the ultimate wild card, a gravitational partner that can turn a predictable stellar life into a spectacular and often short cosmic drama. The elements forged in a star's heart tell the story of its life and death, but some supermassive giants write a far stranger chemical autobiography. Their internal furnaces, running at temperatures and densities beyond imagination, produce bizarre and unexpected abundances of elements that defy standard predictions. This strange nucleosynthesis is a direct window into the most extreme physics occurring within these stellar cores. Two primary processes are responsible for creating the bulk of the heavy elements in the universe, and both are dramatically altered inside a supermassive star. The first is the slow neutron capture process, or S process. Here, atomic nuclei leisurely absorb neutrons one at a time, with days or years between each capture. This allows unstable nuclei time to decay into stable forms before the next neutron arrives. In a supermassive star, the S process occurs primarily in the helium-burning shell, creating elements like strontium, barium, and lead. It is a relatively calm, methodical form of cosmic alchemy. The second process is the complete opposite. The rapid neutron capture process, or R process, is a frantic, violent free-for-all. It requires an environment flooded with an immense number of neutrons, where atomic nuclei are bombarded in a fraction of a second, building up extremely heavy, neutron-rich nuclei before they have any chance to decay. For decades, the primary site of the R process was a mystery, but we now know it is likely tied to the cataclysmic deaths of supermassive stars and the mergers of their neutron star remnants. In a supermassive star's final moments, as its core collapses, a maelstrom of neutrons can be released, creating a perfect, if fleeting, R process factory. We can actually hold the products of these stellar processes in our hands. Primitive meteorites, the leftover building blocks of the solar system, contain microscopic grains of stardust that predate our sun. These tiny specks are literal fossils from ancient supermassive stars, and their chemical signatures are unmistakable. By analyzing them, we find wild overabundances of certain isotopes that could only have been produced in the specific conditions of a supermassive star's death throes. We see the same story written in light. When we spread the light from a distant star into a spectrum, the dark absorption lines reveal its chemical composition. Some stars show incredibly peculiar patterns, with certain elements like europium or platinum enhanced 100-fold compared to their neighbors. These are the chemical ghosts of long-dead supermassive stars, their explosive deaths having seeded the cosmos with the unique elemental fingerprints of their violent internal engines. Even gravity itself can become unstable in the hearts of the largest stars. For most stars, the physics described by Newton is perfectly sufficient. But when you approach the truly monstrous scales of the most massive stellar giants, Einstein's theory of general relativity begins to take over. This introduces bizarre, counterintuitive effects that can push a star toward self-destruction in ways Newtonian physics could never predict. One of the most critical of these is the Schwarzschild instability. Think of a star's core as a constant battle between two titanic forces, the outward pressure from radiation and fusion pushing against the inward crush of gravity. In Newton's world, this is a stable tug of war, but in the realm of general relativity, the energy creating that outward pressure actually contributes to the overall gravitational field. It starts to weigh itself down. The very light and heat fighting to hold the star up begin to act like extra mass, making gravity stronger. It is a vicious feedback loop where the star's own life force ultimately betrays it. This relativistic gravity can trigger strange, violent pulsations or even precipitate a sudden, catastrophic collapse. The core becomes increasingly unstable, like a building where the support beams are secretly made of lead, adding to the load they are supposed to bear. For a star already teetering on the edge, this general relativistic instability can be the final push, the hidden flaw that causes the entire structure to implode. This is not a factor for stars like our Sun, but for hypergiants hundreds of times more massive, it becomes a central player in their brief, brilliant, and violently unstable lives. These titanic engines of destruction must somehow be born, yet their very nature fights against their creation. The formation of a supermassive star presents a fundamental paradox. Its future brilliance is its greatest obstacle. For the moment a protostar begins to shine, its intense radiation pushes outward with enough force to blow away the very gas cloud it needs to feed upon. This radiation pressure should, in theory, rip the stellar cradle apart long before the star can grow to such an immense size. So how do these giants defeat their own physics? Astronomers are exploring two compelling and very different pathways to greatness. The first is competitive accretion, a brutal free-for-all within an incredibly dense star cluster. Picture a crowded stellar nursery, a region like the Orion Nebula but far more packed. Hundreds of protostars are all forming at once, all greedily pulling gas from a shared reservoir. In this chaotic environment, the biggest and strongest babies get the most food. A protostar that gains a slight mass advantage develops a stronger gravitational pull, allowing it to steal gas from its smaller, weaker neighbors. It effectively cannibalizes the cluster, growing fatter while stunting the growth of others. This process can, in theory, build up a stellar titan in a relatively short cosmic time. The second hypothesis is monolithic collapse, a far more solitary and serene birth. This scenario requires a pristine, isolated cloud of primordial gas, almost entirely free of heavier elements. Without the dust and metals that help modern gas clouds cool and fragment, this cloud remains a single, massive, and quietly collapsing structure. There is no competition because there is no one else to compete with. The entire vast cloud, containing hundreds of solar masses of material, funnels inward in a coordinated collapse, directly forming a single, monstrous star. This is likely how the very first stars in the universe were born, as solitary leviathans in the dark. We can see hints of this process in action today. Deep within our own galaxy, in clouds like the Tarantula Nebula, we observe incredibly dense pillars of gas and dust, the kind of environments where competitive accretion could be underway. Meanwhile, advanced computer simulations let us peer into this invisible struggle. These digital models show the ferocious push and pull of radiation pressure against gravity. visualizing how chaotic flows and dense filaments of gas might find a way to sneak through the radiation barrier and reach the hungry protostar's surface. The answer may not be a single path, but a combination where the initial seed of a star forms through monolithic collapse before moving into a dense cluster to bully its siblings and finish its growth through competitive accretion. The birth of a supermassive star is not a gentle process. It is a violent, chaotic, and seemingly impossible battle against its own brilliant destiny. That stellar forge is surrounded by its own creation. The material a supermassive star ejects does not simply drift away quietly. It slams into the surrounding cosmos with spectacular violence. The star's ferocious winds and blistering radiation plow into pre-existing interstellar gas and dust, sculpting the space around it and creating some of the most beautiful and dynamic structures in the universe. This interaction is a titanic shove match between the star's outgoing power and the inertia of the surrounding medium. The supersonic stellar wind acts like a cosmic snowplow, piling up the interstellar material into a dense, expanding shell. The leading edge of this shell is a shock front, a boundary where the wind abruptly slows from millions of miles per hour, compressing and heating the gas to millions of degrees. This hot, shocked gas glows brilliantly in X-rays, while the accumulated shell, now illuminated by the star's intense ultraviolet light, fluoresces in vibrant colors, creating an emission nebula. The physics of this collision also explains bizarre stellar behavior. As the shell expands and its density changes, it can act as a natural dimmer switch for the star. Clumps of dust forming within the shell might drift in front of the star from our viewpoint, causing unpredictable dips in its brightness. Furthermore, the turbulent, shocked gas produces specific and dramatic emission features in the star's spectrum. The most famous of these is the P Cygni profile, a spectral line that tells a clear story of expansion. It shows a bright emission component shifted slightly to the red from the glowing gas moving away from us on the far side of the shell, and a deep blue shifted absorption component from the same gas on the near side, moving toward us and blocking the star's light. It is a direct snapshot of an entire sphere of gas expanding outward. A perfect example of this cosmic sculpting is the Bubble Nebula. At its heart lies a massive, hot star, burning at 35,000 degrees Celsius and blasting out a wind at over 4 million miles per hour. This wind has blown a bubble 7 light-years across, pushing the surrounding interstellar cloud into a delicate, shimmering sphere. The star is not centered within its bubble, however, because the cloud it is expanding into is not uniform. The bubble grows faster into less dense regions, creating that iconic off-center look. This single structure is a fossil record of the star's power, a temporary monument to the force a star can exert on its environment, shaping the very galaxy around it before its own light is extinguished. The stellar nurseries of the cosmos hold secrets that defy our most careful predictions. Young, massive star clusters, those glittering cities of newborn suns, should be governed by a predictable order. Yet when we point our most powerful telescopes at them, we find a population of supermassive stars that simply does not make sense. The number of true giants is often far higher than standard models of star formation can possibly explain. It is as if we walked into a nursery and found a room full of toddlers who are all over 7 feet tall, a statistical impossibility that points to a fundamental flaw in our understanding. The heart of this mystery lies in the Tarantula Nebula within a spectacular cluster known as R136. Hubble's Space Telescope images reveal a dazzling metropolis of stars, but the census is all wrong. There is a startling overabundance of hypergiants, stars with masses pushing 200 times that of our Sun, far exceeding what we thought was the upper limit for stellar birth. The mass distribution is skewed, top-heavy with behemoths where there should be a smooth decline from many small stars to a few large ones. This anomaly forces a radical rethink. Perhaps the answer lies not in solitary births, but in the chaotic social lives of these stars. Rampant binary interactions within the dense cluster core could be to blame. Stars are not born in isolation here, they are born in crowds, and gravitational dances can lead to stellar collisions and mergers. Two large, but not impossibly large, stars could smash together in the cluster's violent youth, forging a single supermassive star that should not otherwise exist. This is a form of hierarchical growth where stars build mass through a series of cosmic crashes, artificially inflating the population of giants. Alternatively, the formation process itself might be exotic. The conditions in these dense clusters could allow for a runaway accretion scenario, where a protostar's feeding frenzy is so rapid and efficient that it bypasses the normal radiation pressure limits, ballooning into a monster before it can even begin to shine properly. The pristine gas in these regions, with its specific low metallicity, might also be a key ingredient, allowing vast clouds to collapse into giants without fragmenting into many smaller stars. The light from R136 is not just a beautiful image, it is a cosmic crime scene, and the overpopulation of Titans is the evidence that our models are missing a crucial piece of the story. What other rules of stellar life are being broken in these crowded stellar metropolises? Even the star-shattering power of a pair-instability supernova has its limits. For the absolute leviathans of the stellar world, those potential monsters exceeding 250 solar masses, a different and even more absolute fate awaits. Their cores are so immensely heavy, the gravitational pull so overwhelming, that the pair-instability process is utterly short-circuited. In these Titans, the core collapses directly and immediately into a black hole. There is no explosive rebound, no grand farewell to the universe. The star's own heart simply vanishes from reality, creating a singularity so greedy that it can devour the entire star from the inside out. This direct collapse could forge black holes of a class we are only beginning to hunt, intermediate mass black holes, with masses ranging from 100 to 100,000 times that of our Sun. These are the crucial missing links between the stellar mass black holes born from common supernova and the supermassive giants that lurk in galactic centers. The formation of such an object would leave a distinctive, terrifying signature. Instead of a brilliant supernova, we might witness only a fleeting red flash as the outer layers fall inward, a dim glimmer before the final darkness swallows everything. The hunt for these phantom births is one of modern astronomy's greatest quests. Where do we look for such impossible stars? Our best clues point to the densest, most pristine regions of star formation, places like the Tarantula Nebula, where the overabundance of hypergiants in clusters like R136 hints that stellar physics might be pushed to its absolute breaking point. Could some of those brilliant points of light be ticking time bombs, destined not for a fiery explosion, but for a silent gravitational implosion? The discovery of a star on the verge of such a direct collapse would rewrite our understanding of stellar death, revealing a final, silent fate for the universe's true giants, a disappearance so complete it defies the very concept of a final blaze of glory. From hypervelocity runaways to stars that vanish without a trace, the sheer diversity of these celestial giants is staggering. We have journeyed past stars that spin themselves into disks, stars that cloak themselves in soot, and stars that die over and over in pulsational fits. Each one of these 30 strange behaviors is a cosmic rebellion, a challenge to the simple rules we once thought governed stellar life. They are not just larger versions of our Sun. They are fundamentally different beasts operating under extremes of physics we are only beginning to comprehend. Studying these bizarre behemoths forces us to rewrite our textbooks, pushing the very laws of physics to their breaking point and beyond. Every new discovery, from a Thorne-Zitkow object to a failed supernova, peels back another layer of the universe's deepest secrets. It reveals a cosmos far more dynamic, violent, and wonderfully strange than we ever dreamed. The next time you find yourself under a clear night sky, look up. Somewhere in that vast darkness, a star is being flung from its galaxy, or two stellar titans are merging into one, or a hypergiant is silently collapsing into a gravitational abyss. Let that wonder sink in. These are not distant points of light. They are the engines of cosmic change, the forgers of the elements that make our own existence possible. If unraveling these mysteries excites you, subscribe for more journeys to the edge of our understanding, where the greatest wonders of space are waiting to be discovered.